When it comes to cartilage, the last of the non-muscle components of the musculoskeletal system, we saw that it behaves a little bit differently than tendons and ligaments. First off, it's made of something slightly different. It's made of largely type 2 collagen. And cartilage also has its collagen fibers kind of arranged in this more complex, less well-organized, three-dimensional, kind of like matrix-like form, as opposed to tendons and ligaments, which have those nice, wavy, aligned collagen fibers. So we saw that cartilage functions to smooth the motion of joints. So as a function of having cartilage in your joints, we saw that coefficient of friction is very small inside of a joint, meaning that it's very easy for joints to glide smoothly relative to one another. In instances of arthritic diseases like osteoarthritis, this coefficient of friction goes up, meaning it's much more difficult to move the joints freely, and that's one of the reasons why it becomes much more difficult to move joints when you have arthritis. In terms of the mechanical properties of cartilage, we saw that it displays, number one, a very prominent toe region. So when you load it, it kind of goes like this. It also has this hysteresis behavior, and it has viscoelasticity, meaning if you load it slowly, maybe it looks like that. If you load it suddenly, it looks like that. And again, that is useful from a shock absorption perspective, although most of the shock absorption in between your joints actually happens in the subchondral bone down here, just because there's more space for that shock absorption to happen. Now, we also saw that cartilage has this interesting anisotropic behavior, meaning if you take a little slice of cartilage out, and maybe up here is the joint surface, and then down here at the bottom is the bone, so bone down here. We saw that cartilage up here is pretty squishy, pretty soft, very much has a toe region and this kind of behavior. But then as we go further down, we start getting a stiffer and less less soft tissue like stress strain curve, all the way until, if we take a sample of cartilage very deep from the surface, meaning close to the bone, we see a stress strain curve that almost looks more like that of bone, where very little or no toe region and much stiffer. Much like we saw how tendons, as they insert into the bone, so as you move along the Achilles tendon into the insertion point in the calcaneus down here, tendons get more and more mineralized. Same thing happens with cartilage. Down here, they're very highly mineralized, they're very stiff, they're very rigid, which is why their stress strain curve looks like that down here. We also saw that cartilage has very little or no blood supply, but it seems to have some ability to heal, and there's something in the second problem set that gets at this idea of making a mechanical argument for why there must be some capacity for cartilage to repair itself. Lastly, we saw that the viscoelasticity and mechanical properties of cartilage have to do with its relatively high water content. So you can think about, if inside this cartilage we have those collagen fibers arranged in this kind of complex matrix, there's water inside of it that's flowing around inside that matrix of collagen, and that gives it some of these interesting mechanical properties. So broadly, that's a broad overview of cartilage.